A 2,000-year-old temple stands untouched while modern buildings crumble nearby. This is not luck. It is the result of ancient seismic engineering, a forgotten genius that allowed megastructures to survive earthquakes for millennia. By the end of this, you will understand the precise secrets that made these stone giants dance with the earth instead of fighting it. How did builders without computers create structures more resilient than our own? What hidden wisdom is locked within the stones of Machu Picchu and the domes of Rome? These ancient sites challenge everything we think we know about strength and survival. What does true resilience look like to you? Dust settles on a stone block that has not shifted for centuries. In a region shaken by countless tremors, an archaeologist carefully uncovers its edges, revealing a truth more profound than any artifact. This is the tangible evidence of ancient seismic engineering. It is not a single technique, but a whole philosophy of construction born from deep observation. For generations, builders in earthquake-prone regions watched how the earth moved, saw which structures fell and which stood, and slowly encoded that wisdom into stone. They developed methods to design buildings that could withstand seismic forces long before the science of plate tectonics even had a name. Experts like Dr. Emily Rodriguez emphasized that these were not accidental survivals. They were deliberate adaptations to a living, moving landscape. This represents a fundamental shift in how we view these ancient cultures. It moves them from being merely lucky or spiritually guided to being brilliant, practical engineers who solved a problem we still grapple with today. The core principle is deceptively simple, yet it challenges everything about modern, rigid construction. Ancient builders did not try to fight the Earth's motion. They learned to work with it. They designed structures that could dance. Imagine the difference between a rigid oak tree in a hurricane and a flexible bamboo stalk. The oak resists until it snaps. The bamboo sways, absorbs the energy, and returns to its place. Ancient seismic engineering often chose the path of the bamboo. It is a philosophy of resilience through flexibility, through intentional movement, and through designing weaknesses that become strengths. This mindset is the first key we must turn to unlock the secrets held within temples, pyramids, and cities that have silently outlasted empires. That philosophy of dancing with the earth began long before the first stone was ever laid. The most resilient ancient structures share a common starting point, a secret hidden in plain sight beneath their foundations. They stand where they do for a reason. In the highlands of Peru, the ruins of an Inca settlement are not found in the convenient, flat valley below. Instead, they cling to a rugged mountainside, their terraces cutting into the solid rock of the peak. This was not a random choice or a defensive afterthought. It was the first and most critical act of seismic engineering, strategic site selection. Ancient builders possessed a geotechnical wisdom we are only now fully appreciating. They understood, through generations of observation, that the ground itself could be an enemy or an ally during a quake. They saw how structures on loose, sandy soil would sink and shatter, while those anchored to bedrock often remained standing. This knowledge of soil liquefaction, the terrifying phenomenon where solid ground turns to a fluid slurry under seismic stress, was encoded in their cultural memory. They learned to read the landscape like a map of future stability. A Mesoamerican city would be carefully placed on a stable limestone plateau, deliberately avoiding the fertile but unstable alluvial plains nearby. The builders were not just avoiding bad ground, they were actively seeking a partnership with the most seismically benign part of their environment. This often required incredible effort. The Inca did not simply find a stable mountain, they sculpted it. Their famous terraces were as much an engineering feat as an agricultural one. By cutting massive stair steps into the slopes, they prevented landslides and created vast, level foundations anchored deep into the living rock. They integrated their architecture into the bones of the earth. This reveals a relationship with the land that was deeply symbiotic. It was an understanding that survival meant listening to the geology, choosing not to conquer the most convenient spot, but to collaborate with the most stable one. This foundational wisdom set the stage for every architectural innovation that followed, creating a solid, unmoving partner for the dynamic dance their buildings would need to perform. The Great Wall of China does not merely rest upon the earth, it negotiates with it, stretching across unstable, quake-prone mountain ranges. Its longevity is no accident of mass. It embodies our first foundational technique, the art of the flexible foundation. Ancient engineers understood that a rigid, unyielding base could be a death sentence. When the ground shakes violently, a stiff foundation transfers every jolt directly into the walls above, like a hammer striking an anvil. To prevent this, they introduced a buffer. Beneath massive stone structures, from sections of the wall to temples in the Mediterranean, archaeologists find carefully laid strata of gravel, sand, and even clay. This was not mere fill, it was a seismic cushion. During a tremor, these granular layers could shift, settle, and compress, absorbing and dissipating a tremendous amount of the earthquake's energy before it ever reached the building itself. It is the architectural equivalent of a shock absorber. This principle reaches a fascinating zenith in the pagodas of Japan, a land intimately familiar with the Earth's tremors. Some of these towering, multi-story wooden structures were built upon foundations of loose stones. When the ground moves, the entire foundation can rock and settle, effectively isolating the delicate pagoda above from the worst of the shaking. This idea is profound in its simplicity. Ancient builders realized that to save the structure, you must sometimes allow it to disconnect from the catastrophe happening below. They created a controlled separation, a deliberate flexibility at the very point of contact with the earth. This is not a sign of weakness, but of sophisticated strength. It acknowledges a fundamental truth that you cannot stop the earth from moving, so you must design something that can move with it. This concept of isolation, born from observing how loose soil sometimes protects rather than harms, becomes the first critical lesson in the ancient seismic playbook. And as we look upward from these intelligent foundations, we find this philosophy of flexible disconnection mirrored and magnified in the very bones of the buildings themselves. The stones of Machu Picchu are not simply stacked, they are woven. Look closely at the iconic walls, and you will see no trace of cement holding them together. The blocks, some weighing many tons, fit with such impossible precision that not even a blade of grass can slip between them. This is not an aesthetic choice, it is our second foundational technique, the deliberate and brilliant use of minimal mortar. In a seismic zone, rigid mortar is a liability. It acts like brittle glue, transferring stress directly from one block to the next until the entire wall shatters under the strain. Ancient engineers in Peru, Greece, Turkey, and Japan understood this intimately. Their solution was to build walls that could breathe. By using dry stone or polygonal masonry, they created structures where each massive block was an independent entity, free to shift, settle, and rotate minutely during an earthquake. The energy of the tremor is not concentrated but dissipated across thousands of tiny, intricate movements. Think of it not as a single solid wall, but as a three-dimensional puzzle with a tiny amount of play in every piece. When the ground shakes, the entire wall briefly becomes a dynamic, clicking mechanism. The stones dance against one another, their perfectly carved faces creating immense friction that locks them back into alignment once the shaking stops. This is kinetic architecture in its purest form, designed for motion. The absence of mortar granted these walls a kind of life, an ability to respond and adapt that rigid modern concrete often lacks. It transforms the structure from a brittle monolith into a resilient community of stones, each one supporting its neighbor through movement, not just through static weight. This principle of flexible connection leads us to an even more sophisticated idea. If individual stones can be designed to move, what about designing entire sections of a building to move independently? This flexible puzzle of stone finds its ultimate expression in a material that seems to defy its own nature. High above Rome, the dome of the Pantheon has watched over the city for nearly 2,000 years, a perfect hemisphere of concrete that has survived countless tremors in a seismically active region. Its secret is not in how its pieces move, but in how they are fused into a single, intelligent whole. The Romans achieved this through a material science so advanced that we have only recently begun to decipher its formula. Their concrete was not the brittle substance we know today. Its legendary durability came from a specific recipe, one that included volcanic ash known as pozzolana, mixed with lime and aggregate. When seawater or groundwater seeped into this mixture over time, a remarkable chemical reaction occurred. It formed rare, interlocking crystals within the material that actually prevented cracks from spreading. This is a complete inversion of modern material science, where a crack in typical concrete is a fatal flaw, a gateway to structural failure. A microcrack in Roman concrete becomes something else entirely. The reactive compounds travel along these tiny fissures and heal them, creating new mineral bonds that are often stronger than the original material. The concrete does not merely resist damage, it actively responds to it, gaining strength from its own minor imperfections. This created a monolithic building material with a degree of flexibility and tensile strength that should not have been possible for the ancient world. Now apply this miraculous material to the form of the Pantheon's dome. That vast, unreinforced shell is not a collection of parts, it is a single, continuous entity. When an earthquake strikes, the seismic energy travels across its entire surface. The dome's perfect hemispherical shape and immense weight work together, channeling those forces downward through pure compressive strength, pushing inward and downward in a stable, balanced flow. There are no weak joints for stress to concentrate on, no rigid connections to snap. The entire structure moves as one, its material flexing at a microscopic level to absorb the shock. The Romans, therefore, solved the seismic challenge from the inside out. They engineered not just a shape, but the very substance of their architecture to be resilient. They built with a material that grew stronger with age and stress, crafting a legacy in concrete that was quite literally designed for eternity. This monolithic approach stands in stark contrast to another ancient strategy, one that embraced segmentation and movement in an entirely different, yet equally brilliant way. While the Romans perfected monolithic resilience, a different philosophy of survival was taking shape across the world. In Japan, a land continuously shaped by tremors, architects embraced a radical idea. They designed buildings not to resist the wind but to become it. A 5-story wooden pagoda does not stand rigid against an earthquake. It sways, a graceful and deliberate dance where every element has a role. The secret to this elegant motion lies not in the walls or the roof, but in a single, central pillar known as the shinbashira. This massive timber column is the heart of the system, but it does not behave like a typical support beam. It is often not even anchored to the ground. Instead, it hangs like a giant pendulum from the upper stories, suspended within the hollow core of the pagoda. When the ground begins to shake, the flexible wooden joints connecting each story allow the floors to sway independently, sliding and rocking in a motion called furring. This might sound like a recipe for collapse, but the shinbashira transforms potential chaos into controlled harmony. As the floors sway one way, the immense weight of the suspended pillar swings in the opposite direction, acting as a counterbalance that dampens the overall motion. It is a brilliant, living system of tuned mass damping, perfected over 1,000 years of observation and innovation. The entire structure becomes a shock absorber, with the Shinbashira as its regulating weight. This is dynamic engineering of the highest order, a testament to understanding that sometimes the strongest response is not to stand firm, but to move with intelligent grace. The pagoda's flexibility is its fortress. It absorbs and dissipates energy through movement, a lesson in harmonious resilience written in wood and joinery. This ancient mastery of dynamic response reveals a profound truth. The most enduring structures are not those that fight nature's forces, but those that have learned to move in concert with them. The elegance of a swaying pagoda stands in stark contrast to another ancient approach, one that finds its strength not in movement, but in absolute, immovable mass. Gaze upon the Great Pyramid of Giza. Its sheer, sloping sides do not dance, they anchor. This iconic shape is a masterclass in geometric stability, an intuitive grasp of physics carved into limestone. While the Egyptian plateau is not a highly active seismic zone, the principles locked within the pyramid's form became a foundational lesson in resilience, one that echoed in the minds of builders across the ancient world. The genius of the pyramid lies in its relentless logic. Its wide, impossibly heavy base creates a center of gravity so low that tipping it becomes almost unthinkable. Every ounce of its immense weight pushes downward, consolidating its hold on the earth. During a tremor, seismic forces are not resisted so much as they are absorbed and channeled. The sloping faces guide any lateral shaking downward, transforming horizontal energy into vertical pressure that the massive foundation is perfectly designed to handle. It is the ultimate expression of passive defense, a monument that says to the Earth's violence, "You cannot move me." But this stability is not just about external shape. Look inside. The pyramid's internal architecture, with its corbelled chambers and relieving arches, showcases a sophisticated understanding of load distribution. These features carefully redirect the unimaginable weight of the stone above away from the vulnerable open spaces within, preventing collapse from the inside out. The builders understood that true strength required managing pressure at every scale, from the grand slope to the individual ceiling stone. So what does the pyramid teach the seismic engineer? It demonstrates that resilience can also be found in simplicity and immutable form. Its lesson is one of consolidated mass, of a shape so fundamentally stable that it becomes a geological feature in its own right. This principle of wide bases and low centers of gravity would be adapted and refined in earthquake-prone cultures, informing the design of massive temple platforms and fortified walls. The pyramid stands as a testament to a different kind of wisdom, proving that sometimes the most powerful answer to chaos is not flexibility, but an unshakable, monumental calm. A wooden temple sways and its joints sing a quiet song of survival. While stone relies on mass or perfect fit, ancient builders in East Asia harnessed the living qualities of another material, wood, and crafted it into seismic poetry. The masterpiece of this approach is the Dugong bracket, an intricate network of interlocking wooden arms found supporting the sweeping roofs of Chinese palaces and temples. At first glance, it resembles an impossibly complex wooden puzzle, a decorative crown where beams and brackets stack without a single nail, but its true purpose is far more profound. Each Dugong joint is a carefully engineered shock absorber. During an earthquake, the seismic energy travels into this wooden skeleton. Instead of being met with rigid resistance, the energy is greeted by a system designed to flex. The wooden components, pressed tightly together by the immense weight of the roof above, rub against each other, creating friction that dissipates the shaking force as heat. The joints themselves are semi-rigid, They can deform, bending and compressing like the knee of a runner, absorbing the impact of a stride, and then, crucially, they spring back. This transforms the entire building into a dynamic, breathing entity. It does not fight the wave of energy, it rides it, allowing the structure to sway and settle without breaking apart. The choice of material here is no accident. Wood possesses a natural tensile strength and flexibility that stone lacks, a quality these builders understood intimately. They selected specific woods for their grain and resilience, creating a perfect synergy between the organic material and the brilliant design. The Dugong system is more than architecture, it is a lesson in harmony, proving that resilience can be woven from flexibility and friction, creating a structure that moves with the Earth's rhythm and always finds its way home. The sound of a hammer tapping stone is the ancient world's first quality control test. In a quarry near Athens, a master mason moves along a line of freshly cut blocks, his tool held lightly in his hand. With each precise tap, he listens. A dull, flat thud means a hidden flaw, a fracture waiting to happen, but a clear, resonant ring that is the sound of seismic potential. This was not superstition, it was sophisticated material science. Before a single stone was placed, ancient engineers performed a meticulous curation, selecting rock not just for its size or color, but for its internal architecture. They were searching for stones with specific crystalline structures, ones whose natural grain and fracture patterns could be strategically oriented to resist the shearing, twisting forces of an earthquake. Think of wood, how it splits easily along the grain but resists force across it. Ancient builders understood stone behaves in a similar way. By carefully studying the bedding planes and mineral veins within a block, they could position it in a wall so its inherent strength was aligned against the expected stresses. A block might be turned on its side, its long grain running vertically to bear compression, or laid flat to better handle lateral shaking. This transforms raw material into a tailored component. The quarry was the first workshop, and the mason's ear was the most sensitive instrument. Now, look at a surviving wall of the Parthenon. Its massive limestone blocks are not randomly arranged. They are fitted together with that legendary precision, but also with a deep understanding of the material's biography. Each block was chosen and placed to contribute to a greater whole that was more than the sum of its parts. Together, these individually selected stones create a monolithic mass, a unified entity with a weight and cohesion that actively resists being overturned. The energy of a tremor meets not a collection of rocks but a single, intelligently assembled giant. This meticulous process from quarry to temple reveals a profound truth. The resilience of these ancient megastructures did not begin with grand design. It began with a simple, resonant tap. It started with choosing the right dancer for the Earth's violent ballet, and then positioning them perfectly for the performance. A master builder's song holds the precise angle for setting a cornerstone. In cultures from the Andes to Anatolia, the most critical seismic engineering principles were not archived in libraries, but carried in melody, verse, and ritual practice. This was a living library, its data encoded in the rhythm of a chant that mirrored the ideal spacing for wall buttresses, or in a ceremonial dance that physically enacted the correct sequence for laying a flexible foundation. The knowledge survived because it was woven into the fabric of daily life and sacred tradition, passed from elder to apprentice through a process of immersive, experiential learning. Each major tremor, while a devastating event, also served as a grueling but unambiguous test. In the aftermath, communities did not simply rebuild, they forensically observed. They noted which corner of the temple had cracked and which wall remained pristine. They saw how a particular joint in the wooden pagoda had flexed without failing. This empirical analysis, conducted over centuries, created a powerful feedback loop. A technique that worked was reinforced and passed on. One that failed was modified or abandoned. This is iterative learning on a generational scale, a slow, cumulative refinement of wisdom born from direct dialogue with the Earth's violence, as historian Dr. Aris Thorne notes. The true blueprint was cultural memory. This human dimension represents the invisible framework, the social and intellectual scaffolding upon which all the physical techniques were built. It was the patience to learn from loss, the collective resolve to build back smarter, and the profound understanding that resilience is not a product you create once, but a process you nurture across lifetimes. The stones and joints are the hardware, but this oral tradition, this legacy of observation and adaptation, was the irreplaceable operating system. It reminds us that the greatest engineering feat of the ancient world may not have been a single structure, but the enduring culture of knowledge that allowed those structures to stand. The forum's worn stones still trace the path of a vanished empire's daily life. Here, beneath the shadow of the Palatine Hill, the true genius of Roman engineering reveals itself not in a single temple, but in the very ground beneath your feet. This was a civilization that thought in systems. Their seismic resilience was not a feature added to important buildings. It was the foundational principle of an entire urban ecosystem. They understood that a city, like a human body, needed a strong skeleton, flexible joints, and redundant pathways to survive a shock. So they built not just for grandeur, but for perpetual motion. Their first systemic defense was the ground itself. Before raising a single column, Roman engineers would excavate deep trenches and fill them with layer upon layer of compacted rubble, gravel, and concrete, creating wide, unshakable platforms called podia. These massive foundations distributed the weight of immense structures evenly and prevented differential settling during a quake. It was like giving a colosseum or a basilica its own stable, artificial continent to stand upon. But the true icon of their systemic strength is the arch. Look at any surviving aqueduct like the Pont du Gard in France. That graceful curve is more than beautiful, it is a seismic masterstroke. An arch naturally redirects the downward force of gravity and the lateral push of an earthquake outwards to its sturdy piers. The stones in an arch are in constant compression, pressed tightly together, a form that becomes stronger under load. When the ground shakes, the arch flexes minutely, its shape channeling destructive energy safely into the earth. It is a shape that turns pressure into stability. This principle was replicated everywhere, from bridges to the ceilings of bathhouses, creating a city-wide network of resilient curves. Yet perhaps the most profound example of systemic thinking lies out of sight, in the city's veins and arteries. The Cloaca Maxima, Rome's great sewer begun over 2,500 years ago, still functions today. Its channels were not built as simple tubes, but in a distinct egg shape. This was a stroke of hydraulic and seismic genius. The curved walls of the egg profile are inherently stronger against surrounding soil pressure, and during ground movement, this shape allows for flex and settlement without cracking. If it had been a rigid, square tunnel, it would have shattered long ago. Instead, it adapted, ensuring the city's sanitation and health persisted through disaster after disaster. This is the holistic lesson of Rome. Resilience was embedded in the water supply, the roads, the drainage, and the public spaces. The failure of one aqueduct meant others could take the load. A collapsed street did not paralyze the city because alternate routes existed. They built in redundancy, creating a networked urban organism where no single point of failure could trigger a cascade of collapse. The eternal city's endurance whispers a timeless truth that the strongest civilization is not the one with the tallest tower, but the one with the deepest, most interconnected, and most adaptable roots. The city in the clouds was built to listen. High on its Andean ridge, Machu Picchu does not conquer the mountain, it converses with it. Every element of this Inca sanctuary, from its staggering terraces to its impossibly fitted stones, was engineered for a single purpose: to become one with the living rock beneath. This is not a city placed upon a mountain, it is a city grown from it, a masterpiece of integrated seismic design. The first and most visible layer of this defense is the terraces. These sweeping, green steps that contour the steep slopes are far more than farmland. They are the city's foundational armor. By cutting hundreds of these flat platforms into the mountainside, the Inca engineers performed a monumental act of geotechnical stabilization. They prevented catastrophic landslides by creating a stepped profile that locks the soil and rubble in place, transforming a treacherous, sliding slope into a series of stable, level foundations. Each terrace acts as a giant retaining wall, buttressing the one above it, distributing the immense weight of the city's structures down and out into the solid bedrock of the ridge. It is the architectural equivalent of weaving roots into the earth, a deep and permanent anchor. Upon these terraced foundations rise walls that seem to defy logic. The iconic polygonal masonry of Machu Picchu, where massive, irregularly shaped stones fit together like a three-dimensional stone puzzle, is the heart of its seismic resilience. Unlike rigid, rectangular blocks bound by mortar, these interlocking shapes create a dynamic, breathing structure. During an earthquake, the stones in these walls can minutely shift, rotate, and settle against one another. The energy of the tremor is dissipated across thousands of these tiny, intricate movements, absorbed by the immense friction between the perfectly carved faces. Once the shaking stops, gravity and friction simply pull the stones back into their original, locked alignment. The wall is not a single, brittle entity, but a community of individual blocks, each one granted a tiny degree of freedom to move, ensuring the whole community survives. Yet the Inca engineers looked even deeper, understanding that water could be a silent saboteur. Heavy rains could saturate the soil behind their terraces and beneath their foundations, increasing pressure and triggering instability during a quake. Their solution was a hidden network of genius, an extensive and sophisticated drainage system. Channels carved from stone run beneath walkways and terraces, directing rainwater efficiently away from the structures. Subterranean drainage layers of gravel and rock were laid down to prevent water from pooling. This hydrological foresight ensured the ground remained stable and dry, preventing the liquefaction that could undermine even the most perfectly fitted wall. It was a preemptive strike against an invisible threat. All of these elements, the terraces, the polygonal walls, the hidden waterways, were not separate projects. They were threads in a single, unbreakable tapestry. The terraces stabilized the slope for the walls. The walls were designed to flex upon the stable terraces. The drainage systems protected both. Machu Picchu stands as perhaps the ultimate case study in holistic ancient engineering. It demonstrates that true seismic resilience is not found in a single clever trick, but in a philosophy of total integration where architecture, hydrology, and geology are woven together into a form that is quite literally an extension of the mountain itself. It is a city that learned to hold on not by sheer force, but by becoming an inseparable part of the very landscape it inhabits. The vast dome of the Hagia Sophia floats like a captured sky over Istanbul, a city built directly atop a seismic crossroads. This architectural marvel has endured for nearly 1,500 years, not by remaining unchanged but by learning to dance. Its survival is a testament to a revolutionary idea that resilience is not a fixed state, but a continuous process of listening and adaptation. After devastating earthquakes in the 6th and 10th centuries caused partial collapses of the original dome, Byzantine engineers faced a monumental challenge. They could not simply rebuild what was there before, for it had proven vulnerable. Instead, they embarked on a series of brilliant modifications that transformed the static monument into a dynamic survivor. Their first intervention was to add massive external buttresses. These stone ribs pressed against the building's flanks were not just decorative supports. They acted as external anchors, bracing the walls against the lateral push of seismic waves, providing a counterforce to the dome's outward thrust during a tremor. But the true genius lies in the transition zone, the architectural magic that allows a circular dome to sit upon a square base. This is achieved through pendentives, the elegant, curved triangular segments of masonry that fill the upper corners of the square. The engineers refined these pendentives to become masterful stress distributors. During an earthquake, they flex and channel the dome's immense, shifting weight down into four massive, resilient piers rather than letting it stress the weaker walls. It is a system designed for graceful load transfer under duress. Perhaps the most subtle yet critical change was in the very fabric of the dome itself. In later repairs, builders used specially made lightweight bricks and a mortar with crushed brick aggregate, creating a shell that was significantly lighter than the original. This reduced the overall dead load on the supporting structures, granting the entire system more inherent flexibility. A lighter dome can sway and recover where a heavier one might crack and collapse. Each major repair in the Hagia Sophia's long history became an opportunity to incorporate new seismic insights. Cracks were studied, failures were analyzed, and the next generation of builders applied those hard-won lessons. The structure became a living document of engineering evolution, its stones recording a dialogue between human ingenuity and planetary force. The Hagia Sophia teaches a profound lesson in humility. Its longevity is not a story of perfect, unchanging design, but of intelligent response to failure. It shows that the most enduring creations are those that possess the capacity to learn, to adapt, and to transform static ambition into dynamic, living resilience. Strength is not always about standing still. The ancient builders mastered a deeper physics, one that understood the true nature of an earthquake's threat. It is not the shaking itself that destroys, but the energy it carries, a violent pulse of kinetic force searching for something to break. The most brilliant insight of these early engineers was to stop trying to block that energy entirely. Instead, they designed systems to let it flow, to transform it, and to let it bleed away harmlessly. This is the core principle of energy dissipation through controlled movement. Think of it not as a wall against a tsunami, but as a series of clever channels that divert the flood. In every technique we have explored, from the clicking stones of Machu Picchu to the swaying heart of a Japanese pagoda, this same physics is at work. The seismic energy enters the structure and is immediately presented with a choice. It can concentrate its force on a single, rigid point and shatter it, or it can be invited to spread out, to be spent on 1,000 tiny, intentional tasks. Ancient engineering always chose the second path, the friction between two perfectly fitted stone blocks as they grind minutely against each other during a tremor. That friction is not a failure. It is a triumph. It is the violent kinetic energy of the earthquake being converted directly into heat, dissipated into the air through the simple act of stone rubbing on stone. The flex of a wooden bracket in a Dugong joint that bend and rebound is another transaction. The energy that could have snapped the beam is instead used to deform the wood temporarily, its natural elasticity storing and releasing the force like a spring. Even the rocking of a foundation on a bed of gravel is a controlled sacrifice. The energy is spent on moving countless tiny stones, on compacting the soil, on settling the base by a few millimeters, actions that absorb the shock before it ever climbs into the walls above. This is a profound redefinition of structural strength. It moves us away from the idea of brute force immobility and toward the concept of intelligent yield. The ancient builders understood that a structure which never moves is an illusion, and when the ultimate test comes, that illusion fails catastrophically. By designing for controlled, reversible movement, they created systems that could survive the test not by being unbreakable, but by being incredibly good at bending. They allowed the building to have a conversation with the earthquake, to answer its force with a graceful, dissipative dance. This principle asks us a fundamental question about our own world. In our pursuit of permanence, have we forgotten the wisdom of graceful movement? Have we built a world that is rigid, silent, and waiting to break, instead of one that can breathe, adapt, and sigh with relief when the storm has passed? A Greek temple's floor plan is a mirror held up to nature itself. Its perfect bilateral symmetry, where every column on the left has a twin on the right, is far more than a pleasing visual order. It is a foundational law of seismic survival, a hidden geometry of resilience. In the chaos of an earthquake, a lopsided or irregular building is a death trap. The uneven distribution of mass and stiffness creates a lethal twisting motion, a torsion that wrenches walls apart and rips foundations from their moorings. The ancient architects intuitively understood this. By designing with strict symmetry, they ensured that the building's weight and its inherent rigidity were balanced perfectly around a central axis. When seismic waves strike, the forces are met with an equal and opposite response from the mirrored half of the structure. This prevents that catastrophic twisting, allowing the energy to travel through the framework in a more predictable, manageable flow. It is the architectural equivalent of a well-balanced wheel, spinning true even on a bumpy road. This geometric discipline extended beyond simple mirroring into the realm of sacred proportion. The famed golden ratio, a mathematical relationship found throughout nature, was not just a mystical symbol for beauty. When applied to architecture, it naturally creates forms with inherent stability, with proportions that resist buckling and sway in a harmonious, integrated way. A column's height relative to its width, the spacing of doorways, the rise of a step, all calibrated to this ratio, resulted in a building whose parts were in a state of balanced tension, each element supporting the others. The beauty we perceive in these ancient ruins, therefore, is not a superficial layer. It is the visible signature of a profound functional intelligence. The serene harmony of a temple facade is the direct result of a cold, hard calculation for survival, proving that in the ancient world, the laws of physics and the principles of aesthetic harmony were not separate fields of study, but two sides of the same stone. The elegance was the engineering. The serene reflecting pool in a Persian garden was not merely for beauty. It was a seismic instrument. Beneath the splendor of ancient palaces, from Persepolis to the Minoan complex of Knossos, flowed a hidden network of genius, a hydraulic system designed to outsmart the Earth's tremors. Water, the source of life, could also be an architect of ruin. The greatest threat was not flooding, but a phenomenon called soil liquefaction. Imagine solid ground turning to quicksand in an instant. During an earthquake, the violent shaking can cause water-saturated soil to lose all its strength, behaving like a liquid. A building's foundation, no matter how perfectly laid, will sink and tilt catastrophically into this sudden morass. Ancient engineers observed this danger and declared war on it below the surface. Their first line of defense was a masterful drainage system. At sites like Knossos, sophisticated stone channels were carved not just to bring water in, but to strategically guide it away from beneath critical structures. These were not simple ditches. They were graded, layered, and designed to keep the foundational soil perpetually dry and stable, preventing the water table from rising high enough to trigger a liquefaction disaster during a tremor. This was proactive seismic engineering, stabilizing the very earth itself before a single stone of the palace was set upon it, but water management extended beyond drainage. Consider the iconic Persian Qanat, a gently sloping underground canal that tapped into mountain aquifers and delivered water across arid landscapes. Its construction was a marvel of geotechnical insight. The vertical access shafts and the tunnel itself were often reinforced and positioned to avoid unstable strata, a testament to understanding how water movement deep underground could affect surface stability. Above ground, the celebrated aqueducts, while bringing life to cities, were also feats of seismic design. Their long, linear form was incredibly vulnerable to the differential movement of an earthquake. The Roman solution, seen across their empire, was to build these waterways on graceful series of arches. As we have seen, the arch is a shape that channels force beautifully. But the builders also incorporated flexible joints made of lead or even wood between stone blocks in the water channel itself. These joints could compress and expand, allowing the aqueduct to flex like a spine during a quake without fracturing and cutting off the city's vital supply. Even storage was engineered for movement. Large cisterns, essential for survival, were often built with slightly flexible plaster linings or segmented designs that could tolerate ground settlement without cracking and losing their precious contents. This holistic hydraulic approach reveals a breathtaking scope of ancient planning. It shows that seismic resilience was never just about the building. It was about mastering the entire environment, about controlling the invisible forces of groundwater and pressure. They understood that to protect the temple on the hill, you first had to command the water in the rock beneath it. This integrated thinking leads us to a final, overarching principle, one that ties every technique together into a single, profound philosophy of survival. The serpent beneath the world stirs in its sleep. Across continents and cultures, our ancestors spoke of giant serpents, dragons, or chained beasts whose restless movements made the mountains tremble. These were not flights of pure fantasy. They were a profound form of data storage, a cultural memory encoded in story. When a myth warned of a serpent dwelling along a specific river valley or beneath a particular mountain range, it was often identifying an active fault line. The allegory transformed an abstract, invisible geological danger into a tangible, memorable character. A landscape described as the serpent's back became a place to avoid for permanent settlement, while a tale of a benevolent earth deity holding the beast still might point to a stable, rocky plateau. This narrative mapping was a survival tool of immense sophistication. It packaged complex geotechnical observations about soil stability, landslide risk, and seismic zones into a form that could be easily remembered and retold for hundreds of years, long before written engineering manuals existed. The story itself became the first seismic hazard map. Rituals and taboos reinforced this wisdom. A sacred grove that was forbidden for cutting might be protecting a slope prone to erosion during quakes. A ceremonial practice of building only on ground blessed by an elder often encoded generations of observed stability. These narratives and rules were not about controlling nature through superstition, but about respecting its patterns through accumulated experience. They ensured a community did not have to relearn catastrophic lessons with each new generation. The myth of the earth-shaking serpent, therefore, is far more than a legend. It is a testament to human ingenuity in knowledge preservation. It represents the moment observation was woven into identity, when the hard facts of survival were cloaked in the enduring power of story, allowing the whisper of the fault line to echo clearly in the voice of the storyteller for centuries to come. A computer screen glows in a modern laboratory, its surface a digital tapestry of interlocking polygons. This is not a video game landscape, but a precise three-dimensional model of an Inca wall, every irregular stone scanned and mapped. Here, the ancient dance of stones meets the cold calculus of modern physics. Engineers are now using tools like finite element analysis, a sophisticated form of digital simulation, to apply virtual seismic forces to these ancient designs. They watch as stress patterns bloom across the screen in vibrant colors, revealing exactly how forces flow, concentrate, and most importantly, dissipate through the intricate stone puzzle. The simulations confirm what the silent ruins have whispered for centuries. The tiny gaps and complex interfaces in polygonal masonry create a phenomenon modern engineers call energy damping. Each micro-slip between stones, each minute rotation, converts destructive kinetic energy into harmless friction and heat. The computer quantifies it, giving a number to the genius of intuition. This validation moves from the virtual to the violently physical in seismic testing facilities around the world. On massive shake tables, replicas of ancient joints, wall sections, and even scaled-down models of entire structures are subjected to recorded earthquake motions. One landmark experiment involved building a full-scale model of a traditional Japanese pagoda's central pillar system on such a table. As the platform shuddered with the force of a major tremor, high-speed cameras and sensors captured the elegant, counterbalancing swing of the Shinbashira. The data was unequivocal. The suspended pillar acted as a tuned mass damper, reducing the peak sway of the structure by a significant, measurable percentage. The ancient intuition of hanging a heavy weight in the center was a perfect pre-industrial application of a principle we use today in the tallest skyscrapers. This rigorous scientific process is performing a vital act of translation. It is building a bridge of comprehension between two languages of knowledge, the empirical, experience-based tradition of the ancient builders and the theoretical, mathematical language of modern engineering. For a long time, the survival of these structures was often attributed to mystery, over-engineering, or sheer mass. Now we have the tools to see the precise mechanics at work, to understand the why behind the enduring how. This is fostering a profound new respect. It moves these cultures from the category of mystical monument builders into their rightful place as pioneering engineers and proto-scientists. Their laboratory was the landscape itself, their experiments were the structures they raised, and their peer review was the relentless test of time and tremor. Each temple that still stands is a published paper in the world's longest-running seismic research journal. This rediscovery is not about claiming we have nothing new to learn, but about realizing we have an immense, forgotten library to consult. It asks us a humbling question. In our rush toward new materials and complex calculations, what fundamental truths about harmony, flexibility, and listening to the earth did we leave behind in the stone? The same elegant dance of wood and stone played out across the ancient world. On a windswept hill in Greece, a master carpenter shapes the end of a timber beam into a precise, rectangular tongue. Half a world away, in the misty forests of Japan, another artisan carves a complex network of interlocking wooden arms. These builders never met, they shared no blueprints, and yet they were solving the same violent equation. Separated by vast oceans and unbridgeable distances, cultures from the Mediterranean to the Pacific Rim arrived at eerily similar answers to the seismic threat. This is not coincidence. It is the convergent evolution of human ingenuity, a testament to a universal logic that emerges when survival itself is the teacher. Consider the profound parallel between the timber frames of a traditional Greek temple and the wooden skeletons of East Asian architecture. The Greek system relied on the mortise and tenon joint, where a carved protrusion, the tenon, fits snugly into a matching cavity, the mortise. This created a connection that was firm, yet not rigidly fused. During an earthquake, these joints could flex, the wood fibers compressing and releasing, allowing the entire frame to sway as a unified, flexible cage. Now look east to the Dugong bracket system of China. Though far more intricate in appearance, its core principle is strikingly similar. It uses interlocking wooden pieces that press and rub against each other, creating friction that dissipates energy while allowing the structure to breathe and move. Both systems rejected the idea of a monolithic, brittle building. Instead, they conceived of architecture as a collaborative wooden skeleton, where the connections themselves were designed to be the primary shock absorbers. This pattern of independent discovery repeats with the concept of base isolation. The Incas built their terraces and foundations to stabilize slopes and allow for settlement. The Japanese sometimes set pagodas on loose stone foundations that could rock. Though the materials and scales differed, the underlying physics was identical. They understood that isolating a structure, even partially, from the direct, jarring motion of the ground could mean the difference between collapse and survival. It was the realization that you must sometimes let the foundation move to save the building above. Even the pursuit of geometric harmony reveals a shared intellectual journey. The Greeks sought perfect symmetry and the golden ratio to create balanced, torsion-resistant forms. The Maya, in their pyramidal temples in Mesoamerica, employed steep, stable slopes and wide bases, achieving that same low center of gravity and resistance to overturning. They were all navigating toward shapes that naturally channeled forces in stable, predictable ways, guided by observation and an intuitive grasp of physical law. What does this global tapestry of solutions tell us? It suggests that when faced with the raw, indiscriminate power of an earthquake, the human mind, regardless of culture or creed, travels down a similar path of reasoning. Observation leads to a core insight. You cannot stop the energy, so you must manage it. From that insight, a set of logical principles emerges: flexibility over rigidity, dissipation over resistance, harmony over irregularity. Different cultures, using the materials and aesthetics native to them, simply crafted different expressions of those same universal principles. This convergent evolution points to a profound truth. The quest for stability in an unstable world is a fundamental human endeavor. It unites the temple builder on the Acropolis with the pagoda carpenter in Kyoto, not through trade or empire, but through a shared dialogue with the very planet they called home. Their legacy is not a collection of isolated wonders, but a single, global heritage of resilience, written in a language of stone, wood, and motion that we are only now relearning to read. A perfectly fitted stone holds a secret it can no longer tell. For every ancient technique we have painstakingly reverse-engineered, there are countless others that slipped into silence, lost in the twilight of empires. The most famous of these vanished arts is the formula for Roman concrete. For over a millennium, the precise recipe that created a self-healing, maritime strength material was simply gone, a casualty of fractured trade routes, shifting priorities, and the slow erosion of specialized guild knowledge. Its rediscovery in modern laboratories is a recent and still incomplete triumph. This pattern of loss echoes across the globe. In Mesoamerica, the foundational wisdom behind certain temple platforms, the specific rituals for soil compaction, or the esoteric choices of aggregate material may never be fully recovered. These gaps in our understanding are not mere historical footnotes. They are stark reminders that engineering knowledge is a fragile, living tradition. It requires a continuous chain of masters and apprentices, of practiced hands and memorized songs, to survive from one generation to the next. When that chain is broken by conflict, cultural collapse, or simply the passage of quiet centuries, the nuance evaporates. We are left with the magnificent, mute result, but not the full conversation that created it. This reality forces us to confront a humbling and tantalizing question. The techniques we have identified, from polygonal masonry to tuned mass damping, represent only the secrets that were both successful and left behind in a durable, decipherable form. What other seismic solutions existed? What subtle adaptations, what brilliant local materials, what now forgotten principles were employed by cultures whose records were on perishable bark, or whose master builders took their deepest knowledge with them? The silent stones of a collapsed pyramid in a seismic zone may hold the blueprint for a dissipation method we have not yet conceived. This sense of profound mystery does not diminish the ancient builders' achievements. It magnifies them. It highlights that what we have managed to recover and verify is likely just a fraction of a much deeper, richer library of human ingenuity. It urges modern archaeologists and engineers to become better listeners, to approach every ruin not just as a puzzle to be solved, but as a fragment of a lost conversation, a single page from a missing manual on how to dance with the earth. The true lesson of these lost techniques may be a call for humility, a reminder that our own modern certainty is but one chapter in a very long story of survival. A modern skyscraper stands upon a set of massive, engineered bearings, allowing it to float above the trembling earth. This is not a rupture from the past, but a direct echo. Those base isolators are the sophisticated grandchildren of the Inca's terraced gravel and the Pagoda's rocking stone foundation. This connection reveals a profound truth. The ancient principles of seismic resilience are not historical curiosities. They are the very pillars of a new architectural philosophy, one that merges durability with sustainability. In an era defined by climate change and resource scarcity, these time-tested strategies offer a vital blueprint, showing us how to build for longevity without imposing a crushing carbon cost on the planet. The first lesson is in material intelligence. Ancient builders worked overwhelmingly with local, natural materials, stone from nearby quarries, timber from surrounding forests, earth from the site itself. This minimized transportation energy, what we now call embodied carbon, and ensured the materials were inherently suited to the local climate and seismic conditions. Their use of flexible wood and breathable stone created structures that managed energy passively, without the need for complex, failure-prone mechanical systems. This principle of passive resilience is a cornerstone of green design today. Imagine a building that cools itself through strategic ventilation like a Persian windcatcher, or whose thermal mass regulates temperature like a Roman concrete vault, all while its flexible skeleton dissipates seismic energy through friction and movement. This is architecture that works with environmental forces, not against them, drastically reducing its operational energy demands. The ancient holistic view of site integration is another critical lesson. They did not see a building as an isolated object plopped onto a landscape. It was an extension of that landscape, its foundations woven into stable bedrock, its form responding to sun, wind, and water flow. Modern sustainable design calls this biophilic or regenerative architecture, where buildings actively improve their local ecosystem. The Inca terraces prevented erosion and created microclimates. A modern building with a green roof and integrated rainwater management does the same, managing hydrological forces while providing insulation and habitat. This systemic thinking reduces a structure's vulnerability to all kinds of environmental stress, from earthquakes to extreme rainfall. Perhaps the most compelling argument from the past is the sheer timescale of its ambition. These builders invested immense effort for results measured in centuries, even millennia. They built for legacy, not for quick return. In our age of disposable construction and planned obsolescence, this long-term perspective is revolutionary. It asks us to value durability and adaptability over cheap speed. A building designed to flex and last for 500 years using local, low-carbon materials represents an ultimate act of sustainability. It avoids the cycle of demolition, waste, and reconstruction that accounts for a staggering portion of global carbon emissions. The ancient world whispers a challenge to our modern one. Can we relearn the patience to build lighter, smarter, and in deeper harmony? Can we design our cities not as brittle monuments to temporary wealth, but as resilient, integrated ecosystems meant to shelter generations yet unborn? The stones of Machu Picchu and the domes of Rome hold a quiet answer. They prove that true sustainability is not a new technology, but a very old wisdom waiting to be remembered. A laser pulse, invisible to the human eye, travels through dense jungle canopy and bounces off a stone wall hidden below. This is not treasure hunting, it is high-resolution listening. An archaeologist stands at the edge of a protected site, her tools not a shovel and brush, but a tripod-mounted LiDAR scanner and a tablet. With each sweep, millions of data points create a perfect digital twin of the terrain, revealing the subtle contours of ancient foundations and drainage channels without a single grain of soil being moved. This moment captures a profound ethical shift in how we engage with these resilient wonders. The very engineering that allowed them to survive earthquakes, their flexible joints and delicate equilibrium with the landscape, also makes them extraordinarily fragile to intrusive methods. A careless excavation can destabilize a terraced slope that has held for 1,000 years. Disturbing the precise arrangement of stones in a dry stone wall can destroy the friction fit that is its seismic secret. The quest for knowledge, therefore, must be tempered by a principle of first, do no harm. Modern preservation has become a balancing act between revelation and respect. Technologies like ground-penetrating radar, drone photogrammetry, and LiDAR allow researchers to read these sites like a three-dimensional book, mapping structural details and subsurface features with astonishing clarity, all from a distance. It is archaeology through remote sensing, a practice that prioritizes the longevity of the site over the immediate extraction of artifacts. This ethical framework recognizes these places as more than ruins. They are open-air textbooks, continuous experiments still yielding data. Their value lies not just in what they were, but in what they still are, functioning systems in a state of graceful endurance. By choosing non-invasive study, we make a commitment to stewardship. We become guardians of a dialogue that began millennia ago, ensuring that the next generation of engineers and historians can stand where we stand and ask their own questions of the silent, enduring stone. This responsibility transforms our role from mere students of the past into active partners in its preservation, understanding that the greatest tribute to ancient genius is to ensure its lessons remain etched not only in our papers, but intact upon the earth itself. The silent dialogue between stone and earth is about to find a new digital voice. We stand at the frontier of a profound synthesis, where the deepest past is guiding the most ambitious future. The next chapter in seismic engineering is not about abandoning our tools, but about expanding our library. It involves reverse engineering not just ancient structures, but the very processes of life and history that inspired them. Imagine a new class of building material born in a lab that mimics the miraculous self-healing properties of Roman concrete. Scientists are already studying how to embed microcapsules of healing agents within modern concrete, so that when stress creates a tiny fissure, these capsules break open and release a compound that fills the crack, just as the Roman pozzolana reaction did over centuries. This is biomimicry and historical mimicry combined, learning from both biological systems and ancient human innovation to create a material that maintains itself. Beyond materials, the very forms of ancient resilience are being decoded by a new kind of apprentice, artificial intelligence. Researchers can now feed thousands of high-resolution images of Inca polygonal joints, Japanese Dugong brackets, and Roman arches into machine learning algorithms. The AI analyzes these shapes not for their beauty, but for their geometric logic, searching for patterns in their success that the human eye might miss. It can then simulate countless variations, proposing entirely new hybrid joint designs that optimize for flexibility, friction, and energy dissipation in ways that blend the best of multiple ancient traditions. This is not replacement, it is amplification. It allows us to test 1,000 years of iterative ancient experimentation in a digital space in a matter of days, uncovering underlying principles that took generations to intuit. This forward-looking synthesis promises a new era of resilience that is both deeply informed and radically innovative. We can envision cities where buildings are clad in bio-inspired facades that flex like scales, where foundations are monitored by networks of sensors that learn a structure's unique vibration signature and predict its needs, and where every new design is stress-tested against a vast digital archive of what has already survived the test of millennia. The goal is to forge an unbreakable chain of problem-solving, where the quiet wisdom locked in temple stones directly informs the algorithms shaping our future skyline. This is the ultimate lesson the ancient builders leave us. True progress is not a linear march away from the past, but a spiral where we return to foundational wisdom with new eyes, ready to listen once more to the enduring whisper of stone. But were these structures simply lucky? A critical voice whispers that perhaps we are seeing patterns where none exist, that the silent survivors are just the fortunate few in a graveyard of forgotten failures. This is the challenge of survivorship bias, a logical trap where we only see the successes, never the countless attempts that crumbled. It is a healthy, necessary skepticism. For every Machu Picchu that stands, how many settlements slid off their mountainsides? For every Roman dome intact, how many collapsed into rubble during that same tremor? The historical record is written by the winners, and in architecture, the winners are those that did not fall. This perspective forces us to ask a harder question. Can we truly call it engineering, or was it just persistent trial and error, with the successful experiments being the ones we happen to find? The answer lies not in a single perfect building, but in a pattern of repeated choices. When the same distinctive technique, like polygonal masonry or base isolation through terraces, appears across dozens of structures within a seismic region, it moves beyond coincidence. It becomes a cultural signature, a transmitted solution. Furthermore, we have fragments of cultural memory that hint at deliberate seismic awareness. Ancient texts and oral traditions from Japan to the Andes contain descriptions of ground shaking and specific building codes or rituals for stabilization. These are not records of random luck, but of observed cause and effect. The most compelling evidence, however, comes from the present. Modern scientific validation through simulations and shake table testing provides the crucial link. When engineers digitally reconstruct an Inca wall and subject it to recorded quake forces, the data shows the precise mechanical advantage of its design. It quantifies the intuition. This does not mean every ancient builder had a full theory of plate tectonics. Their understanding was empirical, born from generations of watching what worked and what did not. They may have explained it through the language of myth or divine favor, but their hands built according to principles that we can now measure and prove. The skepticism, therefore, does not weaken their achievement. It refines it. It pushes researchers to look for more evidence, to listen more carefully to the stones and the stories. It reminds us that history is a grand, incomplete puzzle. Some pieces are forever lost, leaving gaps in our understanding. Yet the enduring debate itself is a tribute to the ancient mind. It forces us to engage with them not as mystical ancestors, but as pragmatic problem solvers whose legacy of resilience continues to challenge and inspire our own ideas of what is possible. The enduring stones ask a question of our own time. In an era defined by rapid change and unforeseen disruptions, from economic shifts to climate events, what deeper wisdom can these ancient masters of longevity offer us? Their legacy is not a manual of forgotten construction tricks, but a profound philosophy of resilience, a mindset etched in stone and timber. The first lesson is the discipline of observation. Ancient builders did not impose their will upon the landscape blindly. They watched for generations, learning the language of the land, understanding where it was stable and where it was treacherous. In our fast-paced world, we are often taught to act quickly, to innovate without pause. But the ancient approach reminds us of the power of patient attention, of truly seeing the system before you intervene. It is a call to listen to the subtle signals in our own environments. Whether in a community, a market, or a personal relationship, before building our plans upon them. From observation flows the second lesson, the power of adaptation. When the Hagia Sophia's dome cracked, Byzantine engineers did not stubbornly rebuild it the same way. They adapted its design, adding buttresses and lightening its load. They treated failure not as a final verdict, but as critical feedback. This is a radical shift from a fixed mindset to a growth mindset. It teaches us that resilience is not about being unbreakable from the start, but about possessing the humility and ingenuity to change course when reality delivers a tremor. The structure that cannot adapt is the one that will shatter. This connects directly to the third principle, the strength found in flexibility. The rigid oak snaps in the storm, while the bamboo bends and returns. Ancient engineering consistently chose the path of the bamboo. It designed systems that could yield, sway, and dissipate energy. For us, this translates to building flexibility into our own lives and institutions. It means creating businesses with adaptable models, communities with strong but decentralized networks, and personal lives that value suppleness of mind and spirit over brittle certainty. The goal is not to avoid all stress, but to develop the capacity to move with it and recover. Underpinning all of this is perhaps the most challenging lesson: long-term thinking. These builders invested immense effort for results measured in centuries. They prioritized endurance over short-term expediency, legacy over immediate return. In a culture often focused on quarterly profits and instant gratification, this ancient perspective is a quiet revolution. It asks us to consider the downstream consequences of our choices, to value durability and sustainability, and to build things meant to last for generations we will never meet. So, what does this mean for us now? These are not merely architectural principles. They are a blueprint for building resilient communities that can support one another through hardship, for creating businesses that can weather economic shifts, and for crafting personal lives of enduring strength. The ancient builders teach us that to withstand the inevitable shocks, we must be willing to move, to learn from what falls and what stands, and to build humbly upon the accumulated wisdom of those who came before. Their greatest gift is the demonstration that a legacy is not a static monument, but a living, adaptable practice, one that learns to dance gracefully with disaster, and in doing so, finds a way to endure. The story of these ancient megastructures is not a relic of the past, but a living conversation with our future. From the pyramids to the pagodas, the enduring legacy of seismic engineering is a testament to human creativity in the face of nature's raw, indifferent power. We have journeyed together through the secrets of flexible foundations and dancing stones, through the cultural memory encoded in myth and ritual, uncovering a forgotten science of survival that speaks across millennia. These techniques whisper a timeless truth that true strength is not always found in rigid defiance. It is often discovered in intelligent yielding, in the graceful absorption of shock, and in a profound, deliberate harmony with the environment. As we navigate our own era of modern challenges, from climate uncertainty to the pressures of an interconnected world, these silent stone teachers offer more than historical curiosity. They stand as beacons of resilient design, urging us to build with patience, to plan for the long term, and to seek solutions that work with natural forces rather than against them. They remind us that the most enduring creations are those that can adapt, that can learn from stress, and that are woven thoughtfully into the fabric of their place. If this exploration of timeless engineering has sparked your curiosity, we would love to hear your thoughts. Which ancient wonder would you most want to see tested against a modern earthquake simulation? Share your ideas in the comments below, and if you enjoyed this journey into history's greatest mysteries, consider subscribing for more. There are always more secrets waiting in the stones.